Hello, my curious friend, and welcome to the Deep Field channel. Make yourself comfortable. Feel the weight of your body sinking into the mattress as if gravity were an extra blanket no one ever told you existed. Tonight we're going to touch on a question that lives at the bottom of every question. A question so fundamental that most people go their entire lives without ever speaking it aloud, even though they sense its outline every time they light a candle, every time they feel the sun on their skin, every time their heart beats without asking permission. The question is this: where does energy come from? You have probably heard before that energy cannot be created or destroyed, only transformed, and that is true. But think about what that really means. If energy can never be created, then the energy burning inside every star, driving every heartbeat, holding every atom together, none of it was ever manufactured. It has always been here. Which raises an obvious problem, almost childlike in its simplicity. If no one made energy, where did it come from? Something had to start the chain, and the answer takes us to a place that physics can barely describe. By the end of tonight, you will understand why this chain stretches all the way back to the very beginning of time, and what that means for everything that exists, including you, lying there with your eyelids growing heavy and the world outside becoming more and more distant. Before we begin, if you enjoy these journeys as much as we enjoy preparing them, leave a like or subscribe to the channel. It is a small gesture, almost automatic, but it helps this space reach more tired and curious minds like yours. If you want to get even closer, consider becoming a member. Members receive early access to our videos. The link is in the description. And to those of you who are already part of our community, my heartfelt thank you. Now adjust your pillow, release your shoulders. If sleep comes halfway through the journey, accept its invitation without guilt. Science will still be here tomorrow. Let us begin. And let us begin with something ordinary. So ordinary that you have probably never stopped to truly look at it. You pick up a ball, hold it at chest height, and let go. The ball falls, hits the floor, makes a sound. That sound is energy. Pressure waves rippling through the air created the instant the ball struck the ground. But where did that energy come from? It came from the motion of the ball as it fell. And where did that motion come from? From gravity pulling the ball downward. And where did gravity get the energy to do that? This is where things start getting interesting. Gravity did not create energy. What happened was a conversion. When you held the ball up high, it had potential energy stored in its position relative to the ground. That potential energy was built when you lifted it, using chemical energy in your muscles. That chemical energy came from the food you ate. The food got its energy from sunlight, from plants converting photons into sugars through photosynthesis. The sunlight came from the sun. The sun got its energy from nuclear fusion in its core, fusing hydrogen into helium and releasing a fraction of its mass as pure energy. And the hydrogen in the sun was assembled in the first few minutes after the Big Bang, when the universe was a hot, dense soup of particles cooling fast enough for protons to stick together and form the lightest elements. In every single step of that chain, no energy was created. It was converted, form after form after form. The ball hitting your floor is, in a sense, the final tip of a chain of transformations, stretching back 13,800,000,000 years. And as you listen to this, as the weight of your body distributes itself across the mattress, consider that every beat of your heart right now is the tip of an equally long chain. The glucose fueling your cells came from something you ate, which came from something that grew using light, which came from a star that has been burning hydrogen existing since the beginning of everything. You are, in this very moment, being carried by energy that is as old as the universe itself. And that is what physicists mean when they say energy is conserved. The first law of thermodynamics declares with an almost brutal simplicity, energy cannot be created or destroyed, only transformed from one form into another. The total amount of energy in a closed system remains constant, always, without exception. It is one of the few statements in physics that no one, in the entire history of experimental science, has ever observed being violated. Not once, not even a little. And that is an extraordinary declaration. Most laws of physics are approximations. They work under certain conditions, break under others, and get refined when better instruments reveal finer details. But the conservation of energy has withstood every test ever devised. Drop a ball, run a nuclear reactor, collide particles in the Large Hadron Collider at energies of 13.6 trillion electron volts, watch a black hole swallow a star, count the energy going in, count the energy coming out. They always balance, always. And yet the deeper question remains, if energy cannot be created, where did the energy that exists in the universe come from? Something had to start the chain. There had to be a first link. And this is where we need to be honest about what we know and where our understanding genuinely runs out. But before we go deeper into the origin of everything, it is worth understanding what energy actually is. Because this is a concept most people think they understand and almost no one truly does. Ask a physicist to define energy, and you will get a surprising answer. There is no clean, intuitive definition. Richard Feynman, one of the greatest physicists of the 20th century, addressed this directly in his famous lectures. He said that there is a numerical quantity that does not change when something happens, and we call it energy. But that it is a profoundly abstract idea, because it is fundamentally a mathematical principle, not a description of any tangible substance. Notice what that means. Energy is not a thing. It is a number that stays constant. It is defined by the fact that it is conserved, not by some deeper essence or substance. We cannot say what energy is the way we would say what a stone is or what a flame is. We can only say what it does. It persists. It transforms. It never appears from nothing and never vanishes into nothing. This circularity bothers some people, but it is also honest. Physics is built on mathematical relationships that work, not on metaphysical explanations of why they work. The honest scientist admits what they do not know, so energy is conserved. It takes many forms: kinetic, potential, thermal, chemical, electromagnetic, nuclear. These forms convert into one another constantly, in every process happening anywhere in the universe. The total never changes. And the question of where the universe's energy originally came from is a question about the origin of the universe itself. And that question inevitably leads us to a woman most people have never heard of, but whose discovery is considered by physicists to be one of the foundations of all modern science. In 1915, a German mathematician named Emmy Noether proved one of the most important theorems in the history of physics. Noether's theorem states the following: every continuous symmetry of the laws of physics corresponds to a conservation law. That sentence deserves to be unpacked slowly. A symmetry in this context means that the laws of physics look the same from different perspectives or at different times. The laws do not change depending on when you perform an experiment. Do a physics experiment today, do the same experiment tomorrow. The results will be the same. That symmetry, that sameness of physics through time, is what Noether proved gives rise to the conservation of energy. Energy is conserved because the laws of physics do not change with time, period. Not because of some mystical property of energy itself, not because some force is maintaining the balance, because of a deep mathematical symmetry at the heart of physical law. If the laws of physics changed from one moment to the next, energy would not be conserved. But they do not change, and so it is conserved. This theorem was so important that Albert Einstein wrote to the mathematician David Hilbert about it, and described Noether's work as the most significant piece of creative mathematical genius produced up to that point. And yet she spent much of her career struggling to be allowed to teach at a university, because she was a woman in a world that had not caught up with what she was doing. Initially, she was not permitted to lecture under her own name at the University of Göttingen. She had to teach under the name of a male colleague. The woman who explained why energy is conserved was, for a time, not allowed to receive credit for her own classes. Physics is strange. History is stranger still. And Noether's theorem does more than explain the conservation of energy. It also explains the conservation of momentum. The laws of physics are the same regardless of where in space you perform an experiment. That spatial symmetry gives rise to the conservation of momentum, and rotational symmetry, the fact that the laws work equally well regardless of which direction you define as up, gives rise to the conservation of angular momentum. These three conservation laws, energy, momentum, and angular momentum, are not independent facts about nature. They are consequences of three symmetries, three deep structural features of physical law, and those symmetries are so fundamental that if any one of them failed, the physics we know would be unrecognizable. Chemistry would not work, orbits would be unstable, machines would not function, the universe would be qualitatively different at every scale. But how did we come to understand all of this? The story itself is a journey worth walking, because it shows how knowledge is built not in heroic leaps, but in small, stubborn steps, sometimes taken by people no one expected. For most of human history, the concept of energy did not exist in any precise form. Ancient philosophers spoke of forces, substances, essences. Aristotle believed that fire, water, earth, and air were fundamental elements, each with a natural place in the cosmos, and that objects moved toward their natural places. This was not physics in any modern sense. It was classification without measurement. The scientific revolution of the 17th century changed the terms of the conversation. Galileo showed that falling objects accelerate uniformly and worked out the mathematical relationship between distance, time, and speed. Newton built on that to develop the laws of motion and universal gravitation, a framework that could predict where the planets would be with extraordinary precision. But Newton's framework did not explicitly include what we now call energy. He worked with forces and accelerations. The concept of kinetic energy, the energy of motion, emerged more clearly in the work of Gottfried Wilhelm Leibniz, a contemporary and rival of Newton. Leibniz argued for a quantity he called vis viva, living force, proportional to mass times the square of velocity. Newton and his followers argued for a different quantity, momentum, proportional to mass times velocity to the first power. There was a significant and often bitter debate about which quantity was the true measure of a body's motion. The resolution came from understanding that both quantities are conserved, but in different situations. The broader concept of energy, encompassing all its forms, took longer to emerge. The key realization was that heat is not a substance. This was not obvious. For much of the 18th century, heat was thought of as a material fluid called caloric. The caloric theory held that heat flowed from hot objects to cold ones, because the caloric fluid flowed from regions of higher concentration to regions of lower concentration. It explained many observations reasonably well, but it ran into trouble with experiments in the 1790s conducted by an American-born physicist named Benjamin Thompson, who later became Count Rumford. While supervising the boring of cannons in Munich, Rumford noticed that the amount of heat generated seemed unlimited as long as you kept boring. If heat were a finite fluid being squeezed out of the metal, it should eventually run out, but it never did. Rumford correctly argued that heat was being generated by the mechanical work of boring. That mechanical motion was being converted into heat. This was the first clear experimental evidence that heat and mechanical energy are interconvertible, that they are different forms of the same thing. The person who made this quantitative was James Prescott Joule, a British brewer and physicist who spent much of the 1840s conducting meticulous experiments, measuring the relationship between mechanical work and heat. Joule built an apparatus in which falling weights turned paddles inside a container of water, stirring it and causing a slight warming. By carefully measuring how far the weights fell and how much the water heated, he determined the mechanical equivalent of heat. How much mechanical work produces how much heat? His measurements were astonishing in their precision, given the equipment available. The unit of energy, the joule, bears his name. Joule's work, along with parallel contributions from Hermann von Helmholtz in Germany, and Julius Robert Mayer, who actually stated the conservation principle clearly first but was initially ignored, led to the formal statement of the first law of thermodynamics in the 1850s. Energy is conserved All its forms are interconvertible. The total never changes. This was one of the great unifications in the history of science. Heat, mechanical energy, light, chemical energy, all brought under a single principle. And the other great unification in the history of energy came from James Clerk Maxwell in the 1860s. Maxwell unified electricity and magnetism into a single theory of electromagnetism. He showed that light is an electromagnetic wave, a self-sustaining oscillation of electric and magnetic fields. This meant that the energy carried by light, which had previously been a mysterious category in its own right, was the energy of electric and magnetic fields oscillating together through space. And it meant that the entire spectrum of electromagnetic radiation, from radio waves with very long wavelengths to X-rays and gamma rays with very short ones, was all the same phenomenon. Different wavelengths, different energies, the same fundamental nature. Maxwell's equations predicted that electromagnetic waves travel at a specific speed, which turned out to be exactly the speed of light. This was one of the most important predictions in the history of physics. It showed that light has a fixed speed, a fact that would eventually lead Einstein to the theory of special relativity. And Einstein's relativity then revealed that energy and mass are equivalent, connected by the equation E equals mc squared, completing the unification of the concept of energy. Mass became a form of energy. The last stronghold, the last category that seemed to be something different from energy, turned out to be energy too. These unifications, Joule's demonstration that heat and mechanical energy are the same thing, Maxwell's demonstration that light is electromagnetic energy, Einstein's demonstration that mass is energy, are each profound scientific achievements, but they share a pattern. Each one takes two things that seem distinct and reveals that they are expressions of the same underlying reality. Energy is the quantity that names that underlying reality. It is what all these different phenomena have in common. And there is something philosophically interesting here. As our understanding deepens, the concept of energy becomes simultaneously more powerful and more abstract. In everyday life, energy feels concrete. You feel it when you lift something heavy. You see it when a campfire burns. You experience its absence when you are exhausted. But as physics digs deeper, energy becomes more and more mathematical. It becomes a number that remains constant, a conserved quantity associated with time translation symmetry, defined not by what it is but by what it does. This is not a retreat from reality. It is a refinement of our description of reality. The most fundamental things, the things that are most deeply true about the universe, tend to be abstract. The force you feel when you push something is, at the deepest level, electromagnetic repulsion between electron clouds in the molecules on the surface of your hand and the object. What you experience as solid, hard, resistant, is fundamentally the mathematical expression of quantum wave functions interacting. The world is no less real for being mathematical at its foundations. It is more coherent, more unified, more describable. And speaking of describable, let us now look at the place where energy becomes most visceral, most tangible, most impossible to ignore. Let us look at the sun, because the sun is where the story of energy stops being abstraction and becomes light on your skin, warmth on your face, the reason morning exists. Every second, the sun converts approximately 600 million metric tons of hydrogen into helium through nuclear fusion. In that process, about 4 million metric tons of mass are converted directly into energy, not released as chemical energy the way a campfire releases it, not transferred from some reservoir somewhere else, converted. Mass becomes energy. The relationship that makes this possible is E equals mc squared, where c is the speed of light, approximately 300 million meters per second. The speed of light squared is an enormous number, roughly 90 quadrillion meters squared per second squared. 4 million metric tons of mass, which is 4 billion kilograms multiplied by that number, gives approximately 3.8 times 10 to the 26th power joules per second. That is the luminosity of the sun, the total power output of our star, measured and confirmed every second without pause for the last 4,600,000,000 years, and for approximately 5 billion more years to come. None of this energy was created. All of it was already there, locked in the mass of hydrogen atoms since those atoms formed in the aftermath of the Big Bang. Nuclear fusion is not a source of energy in the sense of making energy appear. It is a converter. It unlocks energy that was always there, sealed inside matter, waiting. And matter, according to E=mc², is nothing more than extremely concentrated energy. There is no fundamental distinction between mass and energy. They are the same thing. What we call matter is energy in a form that stays still. What we call radiation, light, heat, is energy in a form that moves. Converting matter into radiation, as happens in the core of the sun and in every star that has ever burned, is simply releasing energy from one form into another. The total never changes. And here is something that should make you pause, even with your eyes already growing heavy. The photon that eventually powers a thought in your brain may have begun its journey inside the sun tens of thousands of years ago. The core of the sun is so dense, so opaque, that a photon produced by fusion cannot travel in a straight line to the surface. It bounces, gets absorbed, is re-emitted, absorbed again, scattered endlessly through the dense plasma of the solar interior. The average time for a photon to make that random walk from the core of the sun to the surface, a journey of roughly 700,000 kilometers, is estimated at somewhere between 10,000 and 170,000 years, depending on the assumptions in the calculation. The photons arriving at Earth right now and powering photosynthesis in a leaf may have been generated by fusion reactions that occurred deep inside the sun tens of thousands of years before Homo sapiens existed. Once they reached the sun's surface, they crossed the 150 million kilometers to Earth in about 8 minutes and 20 seconds. 10,000 years inside the sun, 8 minutes in space, then into a leaf, then into you, and as you breathe now, slowly, feeling the air coming cooler and go out warmer, consider that every molecule of oxygen entering your lungs will be used in the mitochondria of your cells to convert energy from food into ATP, the energy currency of the cell. And that energy in the food came from photosynthesis, which came from the sun, which came from hydrogen fusion, which came from the mass of the Big Bang. You are sunlight organized into complexity, temporarily, for a cosmically insignificant interval. And then the organization disperses, the atoms return to the environment, and the energy keeps flowing. Conserved. Always. And there is another angle on energy that most people never consider. The energy locked inside an atomic nucleus. This is a form of energy extraordinary in its density. The nucleus of an atom is held together by the strong nuclear force, the strongest of the 4 fundamental forces of nature, roughly 100 times stronger than electromagnetism at nuclear scales. The protons inside a nucleus all carry positive electric charge, and positive charges repel. Without something holding them together, the nucleus would fly apart instantly. The strong nuclear force does that work. It binds protons and neutrons in the nucleus. And the binding energy, the energy that holds them there, is enormous. To give a sense of scale, the binding energy per nucleon in a typical atomic nucleus is measured in millions of electron volts. For comparison, the energy in a typical chemical bond, the kind that holds atoms together in molecules, is measured in a few electron volts. Nuclear energies are millions of times greater than chemical energies per particle involved. That is why nuclear reactions release far more energy than chemical reactions. Burning 1 kilogram of coal releases approximately 30 megajoules of energy. Fissioning 1 kilogram of uranium-235 releases approximately 80 trillion joules. About 2 million times more energy from the same mass. And that is fission, which converts only a fraction of mass into energy. A pure matter, antimatter annihilation, where all mass becomes energy according to E=mc², would release approximately 90 quadrillion joules per kilogram, more than 1 billion times the energy of burning coal. The difference between chemistry and nuclear physics is not a difference of principle. It is a difference of how deeply you unlock the energy in matter. Chemical reactions rearrange electrons between atoms. Nuclear reactions rearrange protons and neutrons inside nuclei. Matter-antimatter annihilation converts the protons and electrons themselves into energy. Each level goes deeper. Each level accesses more of the energy locked in mass. And speaking of going deeper, let us descend now to the level where energy reveals its strangest nature, the quantum level. In quantum mechanics, energy is not continuous. It comes in discrete chunks called quanta. The energy of a photon is proportional to its frequency, E equals h times f, where h is Planck's constant, approximately 6.6 times 10 to the negative 34th power joule seconds, and f is the frequency of the light in hertz. Higher frequency means higher energy. An ultraviolet photon has more energy than an infrared photon. An X-ray photon has more energy than an ultraviolet photon. This quantization was one of the founding discoveries of quantum mechanics. Max Planck introduced it in 1900 to explain the radiation spectrum of hot objects. Initially, he thought it was a mathematical trick, not a physical reality. Einstein then used it in 1905 to explain the photoelectric effect, the way light knocks electrons off metal surfaces. He showed that energy transfer happened in discrete quanta, photons, not continuously. This earned him the Nobel Prize in Physics in 1921. The implications of quantization extend far beyond light. Electrons in atoms can only occupy specific energy levels. They can jump between levels by absorbing or emitting photons of exactly the right energy. The colours of light emitted by heated elements, the spectral lines, are a direct consequence of these quantized energy levels. Every element has a unique set of energy levels, like a fingerprint. Astronomers use these spectral fingerprints to identify elements in distant stars and nebulae, to measure their temperatures and compositions, to determine the speed at which they are moving toward us or away from us. The chemical composition of the universe has been mapped across billions of light years using the quantized energy levels of atoms. The quantization of energy is not a complication or an approximation. It is a fundamental feature of reality, and it is perfectly consistent with the conservation of energy. Quantized energy levels are stable precisely because you cannot add a fraction of a quantum of energy. You add a whole quantum or nothing. The discreteness of energy is what makes atoms stable. Without it, electrons in atoms would radiate energy continuously, spiraling into the nucleus in a fraction of a nanosecond. Matter would not be stable. Nothing would exist. The quantization of energy is part of the reason the universe can have structure. And there is a relationship between energy and time expressed in the Heisenberg uncertainty principle that is one of the strangest features of quantum mechanics. The more precisely you know the energy of a quantum state, the more uncertain the time associated with that state. A quantum state that lasts a short time cannot have a precisely defined energy. A precisely defined energy requires an infinitely long time to be established. This is not a limitation of measurement. It is a fundamental feature of quantum reality. Virtual particles, the quantum fluctuations that briefly appear and disappear in the vacuum, obey this relationship. They borrow energy from the vacuum for very short times. The more energy they borrow, the shorter the time they can exist. That is why the Casimir effect, the attraction between two uncharged metal plates placed very close together in a vacuum, is real. The fluctuations are real. Their effects are measurable, and the energy-time uncertainty relation governs their behavior. Some people mistakenly use this relation to argue that energy is not conserved at the quantum level, that particles can borrow energy and never return it. That is a misreading. Energy is still conserved in quantum mechanics. The apparent violation is always resolved when you do the bookkeeping correctly, including every part of the quantum system. Virtual particles that borrow energy must return it within the time allowed by the uncertainty principle. They are not exceptions to conservation, they are manifestations of the quantum nature of fields. And as the silence of the room deepens and the sounds outside become more distant, more irrelevant, let us talk about what we cannot see. Because most of the energy in the universe is invisible. Approximately 68% of the total energy content of the universe is dark energy. Approximately 27% is dark matter. Atoms, stars, galaxies, planets, everything we can directly see and touch and measure makes up about 5%. Dark matter is matter that does not interact with light but does interact through gravity. We infer its existence from the way galaxies rotate. The outer parts of galaxies rotate faster than they should if the only mass present were that of visible stars and gas. Something extra is there, providing gravitational pull, dark matter. We do not know what it is. Candidates include weakly interacting massive particles, axions, and various other hypothetical particles that have not been directly detected. It does not emit, absorb, or reflect light. It does not undergo chemical reactions. It only gravitates. But it is mass, and mass is energy. The dark matter in the universe is a vast reservoir of energy locked in an unknown form. Dark energy is stranger. It appears to be a property of space itself, a constant energy density that does not dilute as the universe expands. This is the cosmological constant lambda, which Einstein introduced in 1917 to allow for a static universe, and then abandoned when Hubble discovered the expansion. He called it his greatest mistake. But it turns out there is something there. Not because the universe is static, it is not, but because space has an intrinsic energy density. What is dark energy physically? That is one of the biggest open questions in physics. The vacuum energy predicted by quantum field theory gives an energy density for empty space that is approximately 120 orders of magnitude larger than the observed dark energy density. This discrepancy is sometimes called the worst prediction in the history of physics. It suggests that something is cancelling the quantum vacuum energy almost perfectly, leaving only a tiny residue, and we have no idea what that something is. And all of this brings us back to the heart of the question. If energy cannot be created, where did the energy that exists come from? The answer physics currently offers is this: the total energy of the universe may be exactly zero. This is not a joke. It is not a metaphor. It is a serious, mathematically grounded proposition that some of the most rigorous physicists of the 20th and 21st centuries have explored and defended. The idea works like this. Every piece of matter has positive energy locked in its mass, according to Einstein's equation. A single kilogram of matter contains approximately 90 quadrillion joules of energy, summed across the observable universe. The total positive energy in the form of matter and radiation is a number so large it barely makes sense to state it. But gravity is different. Gravitational potential energy is negative. When two masses are separated by a large distance, they have more energy than when they are close together. Bringing them together releases energy, which means the state of being close is a lower energy state, more negative. The gravitational field of the universe, the sum of all gravitational interactions between every object that exists, contributes an enormous negative term to the total energy budget. Some physicists, most notably Alan Guth, who developed the theory of cosmic inflation in 1980, have argued that when you add up the positive energy of all matter and radiation to the negative energy of the gravitational field, the sum is exactly zero, or very close to it. If this is correct, then the universe did not need energy to exist. It emerged from a zero-energy state without violating conservation, because the net energy of the entire system was nothing. This is sometimes described as the universe being the ultimate free lunch, which is either deeply satisfying or deeply unsettling, depending on your temperament. But even that elegant answer leaves a question open. Even if the total energy is zero, there is still something rather than nothing. There are still the fluctuations. There is still the space where those fluctuations occur. There are still the laws. And the question of why these specific laws exist rather than others, or rather than none, is a question that current physics does not answer. Perhaps it cannot answer. The physicist Sean Carroll has argued that the question of whether the universe has zero energy is genuinely ill-posed without additional context, and that the claim is a somewhat informal way of saying something more technically precise. What we can say without ambiguity is that locally, at every point in space and time, energy is conserved, that locally, matter and radiation obey strict bookkeeping, and that the expansion of the universe introduces subtleties at cosmological scales that require general relativity to be properly addressed. And speaking of environments where energy behaves strangely, let us think about black holes, because they're probably the most dramatic example of how energy conservation holds even in the most extreme places. A black hole forms when a massive object collapses to such high density that its gravitational field is strong enough to trap light. The boundary beyond which nothing can escape is called the event horizon. Inside, space-time is so curved that all possible futures point toward the singularity, the center of the black hole. When matter falls into a black hole, its energy does not disappear. The mass of the black hole increases by exactly the amount that energy dictates, via E = mc squared. The gravitational field of the black hole grows correspondingly stronger. Energy is conserved, but something interesting happens at the edge. In 1974, Stephen Hawking showed that quantum mechanics applied near the event horizon predicts that black holes should emit a very slow, very faint thermal radiation. This is called Hawking radiation. The mechanism is subtle. The quantum vacuum even near a black hole is full of virtual particle pairs appearing and disappearing. Near the event horizon, one particle of the pair can fall in while the other escapes. The escaping particle becomes real, carrying energy. The black hole, which provided the energy to create the pair from its own gravitational field, loses mass slightly. Over an extremely long time, a black hole radiates away all its mass as Hawking radiation and eventually evaporates completely. For a stellar mass black hole, the evaporation time is proportional to the cube of the mass. A stellar mass black hole would take approximately 2 × 10⁻⁶ power years to evaporate. The age of the universe is approximately 1.4 × 10⁻⁻10 power years. 2 × 10⁻⁶ is 57 orders of magnitude longer. Black holes are not going anywhere soon, but eventually they will evaporate, and when they do, all the energy that fell into them will have been returned to the universe as radiation. Energy conserved, transformed from matter and kinetic energy into Hawking radiation over timescales that make even the heat-death scenario seem brief. And if black holes are where energy hides, stars are where it takes shape. Because the story of energy in the universe is in large part the story of stars. When the universe was approximately 380,000 years old, matter and radiation decoupled. Electrons bound to protons to form neutral hydrogen and helium atoms. The universe became transparent. The light released at that moment is still travelling, stretched by the expansion of space into microwave radiation. That is what we call the cosmic microwave background. After that, the universe entered a period called the Cosmic Dark Ages. There were no stars, there was no light, only clouds of hydrogen and helium drifting in the expanding universe, slowly being pulled by gravity into denser and denser regions. Approximately 100 to 200 million years after the Big Bang, the first stars ignited. They were extraordinary objects. Astronomers call them population 3 stars. They formed from pure hydrogen and helium, with no heavier elements, because heavier elements had not yet been manufactured. Without heavy elements to act as cooling agents in the collapsing gas clouds, these stars may have been enormously massive, perhaps hundreds of times the mass of the Sun. They burned extraordinarily bright and extraordinarily hot, and because of their mass they did not last long, a few million years at most. When they exhausted their hydrogen, they fused heavier and heavier elements in sequence, from helium to carbon, from carbon to oxygen, from oxygen to neon to silicon to iron. Iron is the endpoint. When a star's core becomes iron, fusion can no longer release energy. iron fusion consumes energy instead of producing it. The core, deprived of the outward pressure of fusion, collapses under its own gravity in less than a second. What was a core roughly the size of Earth becomes a sphere about 20 kilometers in diameter, compressed to the density of an atomic nucleus. The unfolding outer layers slam into this suddenly rigid core and bounce back. The resulting shock wave is a core collapse supernova, one of the most energetic events in the universe. In those first supernovae, heavy elements were forged for the first time. Elements heavier than iron, which cannot be made by normal fusion, were created in the intense neutron flux of the explosion. Gold, platinum, uranium, iodine, the selenium in your enzymes, all of it. This enriched material spread into the surrounding gas. The next generation of stars formed from that slightly richer mixture. They created more heavy elements, scattered them when they ended. Generation after generation, each cycle enriching the interstellar medium a little more. When the Sun formed, 4,600,000,000 years ago, it formed from gas that had already been processed through multiple stellar generations. Earth, which formed from the leftover material around the young Sun, contained all the heavy elements that had accumulated in the galaxy over billions of years before the Sun was born. The iron in Earth's core, the calcium in your bones, the carbon in every organic molecule in your body, all of it was made in stars that no longer exist. You're made of stardust, but more precisely, you are made of the energy that was locked inside those stars, that was released when those stars ended, that was reorganized over billions of years by gravity, chemistry, and evolution. The energy that moves your muscles now was, in a sense, inside a stellar core billions of years before Earth existed, and that energy, which travelled through dead stars and gas clouds and billions of years of cosmic silence to get here, to get to you, obeys a second law that changes everything. The first law tells you that energy is conserved. The second law tells you that energy tends to become less useful. These two laws together define the arrow of time. They explain why the past is different from the future. They explain why machines wear out, why food cools down, why stars eventually go out, and why the universe, despite containing the same total energy it always has, is in some deep sense running down. The second law of thermodynamics says that in any isolated system, entropy tends to increase. Entropy is a measure of how disordered, how spread out, how many microscopic configurations are available to a system. A concentrated, structured form of energy, like the heat in the core of a star, has low entropy. A diffuse, scattered form, like infrared radiation spread across billions of cubic light-years of space, has high entropy. Energy flows spontaneously from low-entropy states to high-entropy states. Heat flows from hot to cold. Gas expands from compressed to dispersed. Order becomes disorder. You can temporarily reverse this in a local region. Create structure, decrease entropy locally, but only by increasing entropy somewhere else. A refrigerator cools its interior, decreasing entropy inside, but does so by exhausting heat into the room, increasing entropy outside by more than it decreased inside. Every living organism maintains its internal order at the cost of increasing disorder in its environment. We eat low-entropy food and excrete high-entropy waste. We breathe in oxygen and breathe out carbon dioxide. Life is a local temporary decrease in entropy, fueled by a greater increase in entropy elsewhere. In our case, the elsewhere is the Sun. The Sun has low entropy because it is hot and concentrated. It pours out high energy, low entropy photons. Earth absorbs those photons and re-radiates the energy at a lower temperature, higher entropy, in the form of infrared radiation spread across a much wider range of frequencies. Earth radiates approximately as much energy as it receives from the Sun, maintaining a more or less stable temperature. But the entropy of the outgoing radiation is much greater than the entropy of the incoming radiation. That entropy difference is what powers life. In the gap between the concentrated photons coming in and the diffuse heat going out, there is room for complexity, for chemistry, for evolution, for thought. Life is an entropy gradient engine. We are the universe's way of creating local order at the cost of global disorder. Every living thing is a temporary pattern in the flow. And that is not a diminishment. It is the most accurate description of what we are. And here we arrive at something that should steal your sleep, if sleep were not already claiming you. The fact that entropy can increase, the fact that there is somewhere for it to go, means the universe must have started in a state of extraordinarily low entropy. If it had started at maximum entropy, in a state of maximum disorder, there would be no direction for entropy to increase. There would be no arrow of time. There would be no stars, no galaxies, no structure of any kind. The fact that entropy has been increasing since the Big Bang means the Big Bang itself must have been extraordinarily ordered, extraordinarily low in entropy. And that is one of the most intriguing facts in cosmology. Why was the universe so ordered at the beginning? The physicist and mathematician Roger Penrose, who shared the Nobel Prize in Physics in 2020, has argued that the low entropy of the Big Bang is the deepest mystery in physics. He calculated, using his own framework for gravitational entropy, that the initial state of the universe was so special, so extraordinarily improbable in the space of possible universe configurations, that the odds of it occurring by chance are inconceivably small. He writes about numbers like 10 raised to 10 raised to 123 to represent how improbable the initial state was, a number so large that the universe does not contain enough space to write it out in full. Most physicists do not dispute that the initial state was extraordinarily ordered. They dispute whether Penrose's specific quantification is the right way to think about it. But the underlying observation stands. The arrow of time, the relentless increase in entropy we experience, the reason eggs break and do not unbreak, the reason heat flows one way and not the other, traces back to the extraordinary initial conditions of the Big Bang. We experience time moving forward because entropy is increasing. Entropy is increasing because the universe began in a very low entropy state. And why it began in a very low entropy state is an open question, one of the deepest in all of science. Inflationary cosmology, the framework developed by Alan Guth in 1980, and refined since then by many physicists, attempts to address some of these questions. In this picture, the very early universe underwent a period of exponentially rapid expansion. In an incredibly brief interval far shorter than any unit of time we deal with in everyday physics, the universe expanded by a factor of perhaps 10 to the 26th power or more. This expansion smoothed out any large-scale irregularities, which is why the universe looks very uniform on the larger scales. It also amplified tiny quantum fluctuations into the density variations that would eventually become galaxies. During inflation, a field called the inflaton field had an enormous energy density. When inflation ended, that energy was converted into the hot plasma of particles and radiation that became the observable universe. That conversion, called reheating, was where the energy that would eventually become stars and galaxies and planets and people came from. So the energy we see in the universe today traces back, in the inflationary picture, to the energy stored in the inflaton field before the expansion we call the Big Bang. But where did the inflaton field come from? Inflation does not answer that. It pushes the question one step back. Some theories, like eternal inflation, suggest that the inflaton field has no beginning, that it has always existed and will always exist, with bubble universes like ours perpetually budding off from it. In another picture, our universe is one of a potentially infinite number of bubble universes, each with its own physical constants, its own structure, its own history. We cannot observe other bubble universes. We cannot test whether they exist. Other approaches, like cyclic cosmologies, propose that our universe is one phase in an endless cycle of expansions and contractions, with energy persisting through the bounces. String theory and related approaches invoke extra dimensions and additional structures at the Planck scale. The smallest physically meaningful length, approximately 1.6 times 10 to the negative 35th power meters. At those scales, familiar concepts of space and time may not apply. Quantum gravity effects dominate. and we do not have a confirmed theory of quantum gravity. A theory that unifies general relativity and quantum mechanics is one of the biggest unsolved problems in physics. Until we have that theory, the question of what happened at and before the Big Bang and what provided the initial energy remains genuinely open. And the far future of all this energy has a name: heat death. Although the term is somewhat misleading because it implies heat, in a very long time, on scales so vast they make the current age of the universe seem negligible, the universe will approach a state of maximum entropy. Every star will have burned out. Every black hole will have evaporated through Hawking radiation. Even if protons are unstable, as some theories predict, they will have long since decayed. The universe will become a cold, dark, nearly uniform expanse. Energy will still exist, but it will be so evenly distributed that no process can extract work from it. No temperature gradient anywhere, no pressure difference anywhere, nothing to drive any transformation. That is thermodynamic equilibrium, the state where entropy is at maximum. Energy persists but becomes permanently and irreversibly useless, not for a long time, for a time so long that calling it long barely means anything. The current age of the universe, 13,800,000,000 years, is a brief moment compared to the timescales involved in the heat death scenario. We are early, the stars are still burning, the entropy gradient is still steep, structure still forms, life still exists, the universe is still in its youth. And that, my friend, as you sink deeper into your pillow and the world becomes a soft, warm blur, that should be comforting. We are at the beginning. The dance is still full of energy, the music is still loud, and you're here to hear a little piece of it. And there is a concept about energy that matters for everything from designing power plants to understanding why you get tired, and most people have an incomplete picture of it. The concept is efficiency, and it is rooted in thermodynamics. When energy transforms from one form to another, not all of it can be converted into useful work. Some fraction is always lost as heat, which disperses into the environment and becomes unavailable. This is not a problem of bad engineering. It is a constraint imposed by the second law of thermodynamics. The theoretical maximum efficiency of any heat engine, any machine that converts a temperature difference into work, was calculated by the French engineer Sadi Carnot in 1824. He derived what we now call the Carnot efficiency. It depends only on the temperatures of the hot and cold reservoirs between which the engine operates. The efficiency is 1 minus the ratio of the cold temperature to the hot temperature, both measured in Kelvin. A perfectly designed engine operating between a hot reservoir at 1000 Kelvin and a cold reservoir at 300 Kelvin would have a theoretical maximum efficiency of 70%. No engine can do better, no matter how well designed, because thermodynamics does not allow it. In practice, real machines do worse. A modern coal power plant can achieve 30 to 40% efficiency. A modern gas turbine can achieve 50 to 60%. The rest of the fuel's energy content goes out as heat into the cooling water, into the air, into whatever heat sink is available. Not lost in the sense of destroyed, but lost in the sense of useless, dispersed in a form too low quality to do further work. The human body is also a kind of heat engine, but a very sophisticated one. Your cells convert chemical energy in the form of glucose into mechanical energy and electrical signals. The process goes through a molecule called adenosine triphosphate, usually abbreviated as ATP. ATP is the energy currency of the cell. When you need energy for a muscle contraction, a nerve impulse, or a chemical synthesis, ATP is hydrolyzed, broken down, releasing the energy stored in its phosphate bonds. That energy is used to do work. The ATP becomes adenosine diphosphate, with one phosphate group removed. It is then recharged back to ATP using energy from food. A resting human produces and consumes roughly their own body weight in ATP per day, between 40 and 70 kilograms, depending on size and activity level. That sounds impossible because the same molecules are recycled continuously. ATP is hydrolyzed, the energy is used, and the resulting ADP is recharged back to ATP using energy from food. This cycle runs billions of times per second in every cell. The heat you produce is not a malfunction. It is the thermodynamic cost of doing anything. And as you rest now, your body continues generating that heat, maintaining temperature, sustaining gradients, keeping the machine running. 80 watts. A small incandescent light bulb glowing in the darkness of your room, powered by the same energy that moves the stars. And there is something that deserves to be said clearly about the energy our civilization consumes, without politics, just physics. Fossil fuels are ancient compressed biomass. Organisms that captured sunlight through photosynthesis hundreds of millions of years ago, during periods like the Carboniferous, when vast forests covered much of the land and their remains were buried and compressed over geological time into coal, oil, and natural gas. When we burn them, we are releasing chemical energy that was originally solar energy stored for hundreds of millions of years, released in a geological blink. In a very real sense, industrial civilization is a mechanism for converting ancient sunlight into motion, heat, and electricity on a timescale much faster than the one over which it was deposited. We have been doing this for about 250 years. We are burning in centuries what took hundreds of millions of years to accumulate. This is not a political statement, it is a thermodynamic statement. We are drawing down a finite stock of stored solar energy that accumulated over a period roughly 1 million times longer than the period over which we are using it. And all these different energy sources, solar, nuclear, geothermal, tidal, are different windows into the same underlying reality. Energy has been here since the beginning. It has been flowing, transforming, concentrating, dispersing for 13,800,000,000 years. We are not producers of energy. We are managers of transformations, and there is a story that deserves to be told because it shows the absolute power of this law of conservation. In 1930, a physicist named Wolfgang Pauli famously postulated the existence of a new particle never before seen, entirely on the basis of energy conservation. The decay of a neutron into a proton and an electron, a process called beta decay, seemed to violate energy conservation. The electron produced in beta decay did not have enough energy. Some energy appeared to be missing. Pauli refused to believe that energy was not conserved. He proposed that there must be a third particle being produced in beta decay, one that interacted so weakly it had not been detected. He called it the neutrino. He was right. The neutrino, which barely interacts with matter, was experimentally detected in 1956 by Clyde Cowan and Frederick Ranius, 26 years after Pauli predicted it. When they sent Pauli a telegram with the news, he reportedly replied that he was glad he had bet and won. Energy conservation predicted a new particle. The law was so well established, so thoroughly confirmed, that apparent violations of it were taken as evidence that something new must exist, rather than evidence that the law was wrong. And the law was right. The neutrino exists. Energy is conserved. And now, my friend, as the night deepens and your body already rests heavy on the mattress, with that softness that precedes true sleep, let us gather all the threads. The story of energy in the universe can be told as a story of decreasing usability. The Big Bang, or whatever preceded it, was a state of extraordinarily high energy density and extraordinarily low entropy, as organized as it could be. From there, everything has flowed toward greater disorder, greater entropy, more dispersed forms of energy. But the flow is not uniform, it is not smooth. In certain places, under certain conditions, energy accumulates, it concentrates, it organizes. Gravity pulls matter together, converting gravitational potential energy into kinetic energy and heat. That heat fuels nuclear fusion. Fusion produces the heavy elements and radiation that make planetary chemistry and life possible. Life concentrates energy from diffuse sources into the highly structured chemistry of living cells. Intelligence concentrates information and uses it to direct the flow of energy with increasing precision. Each of these is a local decrease in entropy, a local creation of order, fueled by a greater increase in entropy elsewhere. The Sun increases in entropy as it fuses hydrogen. Earth exports entropy to space as it radiates heat. Life increases the entropy of its food as it converts chemical energy into heat and mechanical work. And through all of this, the total entropy of the universe increases inexorably, following the second law with absolute fidelity. The law does not know about us, it does not care, it simply operates in every particle, in every interaction, everywhere, always. But here is what strikes me as most profound in all of this. The universe did not have to do anything interesting on its way to maximum entropy. There is no thermodynamic requirement for stars. There is no thermodynamic requirement for planets, for chemistry, for biology, for consciousness. The universe could have dispersed its energy evenly long ago and reached equilibrium without any of the structure we observe. Why it did not is partly a question of timescales. The processes by which energy concentrates and disperses take time, and the universe has a finite age. And partly a question of initial conditions. The low-entropy Big Bang created a situation where gravity could pull matter into dense regions before thermal equilibrium was reached. But the result, the improbable, detailed, haunting result, is a universe full of structure, full of stars burning for billions of years, full of planets with chemistry, full of organisms that think, full of beings who have existed for a cosmically negligible time and have already managed to trace the chain of energy transformations back to the first fractions of a second of time. That is what we have done. That is where we stand in the flow, temporarily organized from the same matter and energy that has been here since the beginning, aware of our own existence, capable of asking the question. And the answer to where energy comes from, in its fullness, is something like this. Energy did not come from anywhere. It has always been here. The universe did not receive its energy from outside itself because there is no outside. The universe is everything. Space, time, matter, energy, the laws of physics. All of it came with the universe. Or more precisely, all of it is the universe. Before the Big Bang, to the extent that before has any meaning, there was no energy because there was no time for energy to exist in. At the Big Bang, time and space and energy came together. They are not separate things that came from separate places. They are different aspects of the same thing, the universe, and the energy that is in the universe has been here ever since, transforming, flowing, always conserved, never manufactured, never destroyed, just here, as it always has been, as it always will be. It could not have come from somewhere, because somewhere requires space, and space itself came with the universe. It could not have come from some earlier moment, because earlier requires time, and time itself began at the Big Bang. As far as our physics can tell, the energy of the universe is not a consequence of the universe. It is, in a sense, what the universe is. And whatever it was at the very beginning, in a state our physics still cannot fully describe, it has been transforming ever since, through stars, through you, through every process that has ever happened. Changing form, always conserved, always here. And now, my curious friend, tonight's journey is coming to a close. All the threads are on the table. The question has been asked, explored, turned over from every side, and the answer we found is not a period. It is an understanding, a way of inhabiting the mystery without needing to solve it. Energy did not come from anywhere because there was nowhere for it to come from. It is the very fabric of existence. And every transformation it undergoes, from star to photon, from photon to leaf, from leaf to blood, from blood to thought, is the universe talking to itself through the differences it contains. You are part of that conversation. Every cell in your body is right now transforming energy. The mitochondria inside each cell are breaking down molecules and extracting the energy stored in their bonds, converting it into processes that keep the heart beating, the lungs expanding, the brain forming its last conscious thoughts before sleep. The energy sustaining you in this moment came from a star 150 million kilometers away, which has been shining for nearly 5 billion years, burning hydrogen that has existed since the first moments of the universe. You are the universe's energy in the form of consciousness. You are the primordial difference that, after an immensely long and elaborate path, found a way to look at itself and ask where it came from. And as you rest, this energy continues its quiet work. It continues in the cells that repair themselves during sleep. It continues in the stars fusing hydrogen into helium in the dark of space. It continues in Earth's core holding its ancient heat. It continues in the sun that has already begun illuminating the other side of the planet, while here the night deepens. You are safe. The universe takes care of you the only way it always has, by keeping the flow going, sustaining the difference that you are, ensuring that the energy animating you remains accounted for and present. The same law that governs every transformation is the same law that governs your rest right now. The same order that keeps the stars in their places is present here, in this space, in this stillness. Let the weight of the day dissolve like heat dispersing from a warmed surface. Let your thoughts become less sharp, less urgent, more distant. Let your breathing find its own rhythm, that rhythm your lungs have known since before conscious memory. The universe does not need you awake to keep going. It will continue this dance while you sleep. Energy will keep flowing, transforming, sustaining everything that exists without creating or destroying. Conserved, always. In every second of the 13,800,000,000 years that have already passed, and in every second of those yet to come, the stars continue their fusion, the oceans continue their tides, Earth's heart continues its warmth, and you rest inside all of it, part of all of it, made of all of it. The universe continues its silent dance and we rest in its embrace. Thank you for walking with me tonight. Sleep well.